Click the bell icon to get latest videos from Ekeeda.
Hello friends, today we will talk about the transformation of relational expression. That is how we can translate a relational expression into an equivalent expression. For that we say the equivalence rule, then we will look about the transformation, and then we will solve about different position that how we can transform to a relational expression, and we can see that in a designed expression. Now that we have know how to write in a relational algebra expression for solving a query, but we do not use that expression in a practical world. So we need to transform it into some way more applicable and accepted by the user-oriented designers. So we need the transformations to be take place. Now to relational expressions are equivalent if they follow the following rules of the equivalence. Now, if the equivalence is satisfied, then we can easily transform the relational expression to our desired user expression. Now, if we talk about a multiset expression or the multiset attribute, then two multiset attributes onto relational expressions are equivalent if they generate the same tuple for the same multiset values in two of the relation based on a same condition. Say suppose the instructor and the person has the same multiset values, that is phone number. So the phone number can got the home or the work phone number, and if the instructor and person is the same one based on the condition that they belong to Kolkata in some address, now the contact number of this instructor and the person that we are talking about should match with each other. We can only say they are equivalent if they match with each other in every legal database they generate from this multiset attribute. Now we will define some other rules of equivalence to the relational expression. Now the first rule is the equivalence rule for the two relation, that is theta joining. If there is two relations E1 and E2 that belongs to a theta join, then we say that it is equivalent to the theta joining of E2 and E1. So if E1 and E2 are theta join equivalent, then it must satisfy that either side of it belongs, it will generate the same result. If we have two results on this E1 and E2 joined with the other one as E3, that means we have the result of join and E3 as the join of the final join. Then it will be equivalent if and only if we can have E2 and E3 joined with each other, and then we can have E1 joined to it, equivalent result. So these two are equivalent with each other if they produce the same result. Now if we join two results on this set E1 and E2 and then give us selections on this projection, then we say that it is equivalent to, that is E1 having the selection and then joined with the E2. Now we will move to the next section with the equivalence rules other than these three. Now we can denote the predicate also as L1, L2, L3 while we have the joint conditions theta 1, theta 2 and theta 3. Now if we have this situation, that is theta of, so we have the selection of two conditions and then conjunctly behave with this E1, then it is said to be equivalent if it produces the same result with one having the condition with E1, and this from the relational set we can have the selection on theta 1. Now we can represent it in a materialized way like, so this will produce the same result if they are equivalent to each other. Next is the commutative. That means if we perform the selection on this E1 on a theta 2 condition, and from that selection we are selecting on a theta 1 condition, so it will produce the same result if they are equivalent to the situation that we are selecting on a theta 1 condition first, and then based on the input we are covering the theta 2. So if we have the E on theta 2, and then we can have the E of theta 1 on the C. So it will be same like if we have E on theta 1 and we have the theta 2 selection as the result. So this two will be same. Now if there is a sequence of predicates that we are operating on a query or a relation, it will be same as resulting on a predicate that is a combination of all L and this performance on this E. So here we can see that all the combination of L1, L2 to Ln can be combined into the final operation L as the selection on this E is made and then projection of the particular result. This is also called cascadation of this predicate. So the cascade predicate means all the predicates will be combined into the final predicate. Now we can have it as this equivalence. Next is the Cartesian product on this theta join. So we can have that if theta join on the selection E1 and E2 we are making a Cartesian product, then it is same as theta joining on these two relations. So we can say if there is E1 and E2 and then we are performing the Cartesian product on it, then we can select on this theta now which is equals to the joining on this E1 and E2. So it is equivalent on this theta joining on the Cartesian product. Now it is also can be written in a different way. Now the Cartesian product can also be written like in theta. See for the theta joining on E1 and E2 and based on the selection on theta 1. And now it can also say that the selection of theta 1 over the joining of theta 2 can be said the joining of theta 1 conjunctive with theta 2. So this can be written as so there is one join against the join and the selection product. Next is the associative one. The associative one in a simple joining we have already explained. Now we will go for the associative one in the theta joining. See here the associative that we have made the E1 and E2 theta 1 join and then join the conjunctives of the theta 2 and theta 3 with E3. Now we can have with the E1 conjunctive with theta 1 and theta 3 and finally we can have this conjunction with the theta joining on 2 of E2 and E3. Now how can we write this one? See in this 2, here the next level on the parent level or E2, E3 and E1, E2 both has this single join on a theta and on the root level we can have the conjunction on 2 and 3 and here 1 and 2. But the conjunction changes on this ordering is not permitted. So here we cannot put theta 1, theta 2 and theta 3 while having theta 1 and theta 2 here conjunction and 3 here. So the order of that placement should be mentioned. Next is the distribution of the selection attributes. Well, the distribution of the selection attributes that theta 1 from E1 only and theta 2 that belongs to E2 only. So no theta 1 can belongs to E2 and no theta 2 can belongs to E1 for the distribution of the selection on this equivalent operation. Now this one says that we can have the E1 and eta 2 theta join with each other, and the selection is based on theta 1 from eta and theta 2 for E2. Now it is same like if we have selected theta 1 from E1, that is theta 1 belongs to the E1 and theta 2 belongs to E2, and then join them. So now my theta 1 projection on the E1 and theta 2 from this E2 has been joined into this theta join. So that is the distribution of the selection from two relation. Next is the projection operation under this theta joining. So like the selection also, we can also have the attributes from a relation, that is a L1 belong to E1 and L2 belong to E2. So the projection of L1, L2 is in union of the projection on E1 theta join with E2, whereas it is equivalent to if we project the L1 from E1, project the L2 from E2, and then make the theta join. So the selection and projection distribution over the theta joining is same. Say here we have made the union of two attributes and then make the projection on it. So now we have this E1 that is projected on the L1 attribute, E2 that is projected on the L2 attribute, finally joining them with a theta join. Now we have one more definition of this theta joining over the projection. Now say there is one intermediate attribute for each on this E1 and E2, that is L3 for E1 and L4 for E2. So we have projected the L1 L3 combination from E1 and then L2 L4 combination from E2, theta join them, and then make the projection on L1 and L2 from this joint relation. Well, it will be equivalent to all the joint relation on the attribute on union L1 and L2 from this E1 theta joining E2. That means if there is also an intermediate attribute operation on the projection, so the final operation will only have the attributes that belongs to both on this set. So first we have from the projection L1, L3 on E1, L2, L4 on E2, make a theta join that will consist L1, L3, L2 and L4 both. And now we are selecting only the L1 and L2 combination from this joint relation. So which is equivalent to the L1, L2 projection on this theta join of E1 and E2. Next are the set union and intersection operations. Well, they are commutative for this union and intersections both. So that we can represent it as that E1 and E2, if they are joined on an union relation, so it is equivalent to E2 and E1 joined on an union, because they will have only the intersected values. Same for the intersection, they will have all the values that belong to E1 and E2 in both of these cases. As it is more attribute oriented, so the ordering is not necessary. Now the selection operations distributes over the union, intersection and set difference operation too. Now let us see on the set difference operation. Say if we have selected one value on this P on E1 and same value for this E2 and then make the set difference that all the values that belongs to E1 but not this E2, as we are selecting over a single predicate P, so it will give us the same value of E1 minus E2 if we are set differencing it and then selecting P to the predicate. Now the next part will consist that even if we have selected the E1 minus E2 on some predicates and we have selected the predicates from E1, then we have subtracted only the E2 from it, then also it will remain the predicates that is belonging to E1 but not to E2. So the selection of predicate of E2 is become redundant in this expression. Because all the values we have selected from E1 based on this predicate P will consist only the predicate P selections. So now when we will subtract this E2, that will contain on the predicate P and also other values. So all the values will be subtracted along with the values that present in E2 but not in E1. Now it is same as subtracting the E2 from E1 and then selecting the P predicate. Now the projection operation also distributes over the union operation. That means if we project something on this union of E1 and E2, it will be same as projecting E1 projecting E2 and then unioning it. So first we are having E1 and E2, making union out of them, and then we are selecting some predicates L over this union. Now it will be same as if we can select some predicates L and also select the same predicates from E2 and then make their union. So it is also distributed over the union expression. So this is all for the equivalence rules that we have described. Now we will move to the next part that we will see and solve these equivalence rules to actually transform the relational expressions. Now we will take T of this relation. One is instructor, the teachers, and the department. Now for our simplicity, as department also will have the course, we are taking only the instructor, teachers, and course. So now we will see and solve some queries on a relational expression to it. Now say we want to select the name and title from the instructor which teaches some particular courses from the instructor, teachers, and courses relation joined with each other. So now we will transform the expression into a more detailed simple expression on a relational expression. So first our question was, now let us see that name title projecting it from the department chemistry, that is a selection predicate, with the instructor joined with the teachers, that is joined with the predicates over course ID and title, that is projected from the course relation. See, in this way we can have only the final projection because we have one joining, two joining, selection and projection. So we can transform into some relational expression which will generate a smaller intermediate query so that the query processing become optimized, because if there are smaller number of queries as an intermediate processing, we can deliver the error handling more faster and smoothly. Now we can imply our equivalence rules to solve this query transformation. Now let us look at this relational expression. These two are equivalent to each other, but the second one will generate more smaller number of queries, because now we are using that if there is any projection E1 theta joining E2 E3, then we can say that theta joined on this particular projection L1 joining with this other joint portion will be the same, that is distribution over the selection and projection supported by the relational expression. So now we can first select the chemistry from the instructor, because the instructor's department is more concerned here. So we can select the department from the instructor and then join the teachers and course ID projection. So here the course ID projection is the number 1. We can have the teachers joining with the number 3. Then this one joining is the number 3 or the 4, as the instructor being selected with the department came. So this is 3, this is 4, and finally the projection is 5. But here, until and unless we have performed this one, we cannot have any work done. So now we have transformed our first relational expression into an optimized one. Now let us look at some more complex problem. Now the original query becomes more restricted with the course that is being taught only in year 2009. That means one more query predicate there will be for the year 2009. Now see, we have used that L1 conjunct with L2, that is a selection that we are making with the instructor joined with teachers and the projection on the course. So here we can apply the rule of associativity on this natural joining on a selection. So we can just break this instructor join theta join with the teachers and course to the teachers course and along with the instructors that is selected over the conditions department name music and year 2009. So now we can break this instructor join is teachers and course to be transferred into instructor join teachers joined the projection, so that we can have the projection finally before has joining is made to the teachers on this course. So the instructor joined teachers is there because the department name music and the year 2009 belongs to the year and department of this teachers and instructor, while we can project the CID and title from course. So we have made this explanation. So now our resulting query on the transformed relational expression will be So here I have made this selection on the joining instructor and teachers and then make the join on the projection of course. So we are having also now 1, 2 and 3 of the smaller or queries, and this one we had 1 and 2. So we are breaking it as much possible as in the number of the intermediate sections on the queries so that we can have a better result. Now let us look for some other queries. Now let us look at the sub-expression. Now the sub-expression from the last query that we have solved, see there are multiple ways to divide and transform it into other relational expression. So how we can do that? First, we can perform the commutative rule. Now, the commutative rule suppose that this year 2009, if this selection is made on this instructor teaches, and then we can perform the department music selection, then also it will give us the same result. And here we have 1 and 2 number of intermediate operations, while here we have only 1 number of intermediate operations. Now we can even write is that the department belongs to the instructor relation and the year belongs to the teacher's relation. So we can make the selection on this department on the instructor join with the selection year on the teachers. So here also we have one selection for the teachers joining with this 2 selections. So now which one to choose among this, because this will intermediate queries 2 number of both the cases. So an equivalence is said to be minimal if there can be no rule derived from any other combination of this theme. So here we can say that this is not minimal one because we can derive from these 2 combinations one rule, that is one is the associativity, another is the commutative rule for this joining. So both of these rules can be derived from these 2 equivalent combinations. So now we need to find a minimal of this query or the minimal equivalent query so that we can achieve that only one rule can be derived from any of the combination that we are all talking about. Now let us see that what expression which we have in a tree-like structures for the minimal expressions or the tree with multiple selections. So this is our basic tree that we are first fetching the course with the selection on this course ID and title. Make this projection teachers with this join. Make this joining instructor with again a join. Then select the department music in 2009 from it. From the resulting selection, we are production, the name and title. Now what happens if we provide multiple selections to it? Now, while having this multiple participation, we have all the relations as the leaf nodes of our trees. Now we can perform any projection and selection to each of this relation. Then we can join based on the selection or the projection. So if we perform the multiple transformations on this one, that we have transformed this 2 onto the instructor and teacher selection, then made the joining to finally project the name title, so that we can have the minimal expression that there is no rule that can be derived from any other combination of this one. This is the farthest expression that we can transform into the smaller query. Now let us look at some more expression and then form a schema from it to go for the minimal expression. Now from this relational expression, if we take only this part, that is a sub-expression. Now for every intermediate query and the resultant relation will have a schema to it. So for this sub-expression, we also can have a schema. So the now schema will be represented as the department from the instructor and this teachers or the relation on the teachers. So we can have all this ID name, department, salary, and course ID, section ID, semester, year as a combination. But here we will having the redundant information as the part of this query that has been not transformed on. So we need to make a schema in this way that the attribute in the resultant information will either belong to the need of the particular projection or selection, or we can inherit it from the other one, that the ID name and department will be the key to select with these teachers. So the course ID and the section ID, semester, year along with the department will be the schema and the desired one for the minimal expression. So to have this one, we can transform our query to now let us look at this one. First of all, we are having the projection, that is the course from CID and title. So this is number one. Now we are having the department music on instructor and that is joined with teachers. So that is number two. Now we only want from this department and teachers the name and CID, because the CID is enough from this course to generate the title and the name from the ID on that particular department. So why we are not referring to ID but the name? Because the department instructor is already being involved in this selection on the joining, but the CID on that instructor teachers joining can be referred to the title to the course. That is why we have selected CID and name only for the selection on the projection. So if we find the projection name CID on the join on instructor based on the selection music with the teachers and that join with this course relation, then we will have the name, CID, department, and from this course ID we can fetch the title. So other than having all this, we will have only name, department, and CID to have the minimal expression schema. So in this way, we can transform the operations on a relational basis to a subsequent query that will perform the minimal expression, also the schema that is suitable for storing all the having values with the referencing attribute that can go for the reference relation. Now we will talk about join ordering, that how the ordering on the join depends on transformation of the relation. So we know for any natural joining, the ordering doesn't matter. So that is R1 joined with R2 and R3 will be equals to R1 joined with R2 and then finally joined with R3. So now our expression that we have taken, so now it doesn't matter that we perform the teacher's courses joining along with the instructor or the instructor teaches joining with the course. So we will join the following attributes and then see what are the replacements that we can perform on this query. Now in the step 1, we can join the teachers and the projection of CID and title for course. And in the step 2, we could have joined the instructor, that is the selection of music department with the instructor of step 1 and step 2. Now it is quite largely to have the result of replacing it with Now if we join this teaches with the course, then it will be generate each tuple for the course taught. Now if we join the teachers with this instructor, then it will first select the music from the instructor and then generate the tuple for the instructor, which only from the department music and their corresponding courses. So not only the ordering, that the commutative nature, it behaves like this. So we need to talk about that what the possibilities of the resultant tuple or the number of tuples are. If it is generating a more tuples than a possible condition which is on the same level, we should choose the minimal number of changes to this one, because the tuples we are generating here will be much lower than this one, because it will generate a large number of tuples for each course having the taught relation. Now, how can you select between the joining on the ordering? We can select the selection projection combination. If there is a selection with any joining, then we should join it first before joining to the projection. Before can select actually minimizes the relation by selecting some of the attributes to it, and the projection only just gives the result to the output. So the joining will be first done with the selection, next with the projection based on the demand on this query. So here we have made the selection instructor join with teaches, and finally that joined with this course. So we can just include this much together along with this one. Now also the ordering of the attributes in a query would do not matter, but when joining it to the other relations, it matters between the ordering of the attributes in a query. So it also is a result of a direct on a join operation, that how we are joining. If the left is joined with the right one, then the left one will appear first and the right one will appear second. So even if the condition satisfy that R1 joins R2 is equals to R2 joins R1, but the ordering of attribute is not mentioned. Thus when we have So we do not have any common attribute between the instructor and the course, that is got the ID, name, department, salary, and the course ID, title, credits on this course. So we will have, if there are a number of attributes in instructor and b number of attributes in course, a product b number of attributes in this joint relation. And if there is c number of attributes that belongs to teaches and the common attributes from A and B, then we will only have the common attributes from the selection of A into B, comma C. So that is always better to join the attributes if there is a common one between two relation. So it is always go for the instructor teaches relation combination, then go with this course, because we have selected the instructor and teaches joining over the joining of CID and title. Now that the projection course ID and title, if it is not mentioned here, then it is absolutely fine, because course has also got department and instructor has also got department. So there is at least one common attribute which can be reduced to the number of attributes in the resultant relation. So not only the order of the joining, also the order of the attributes matter when we have the course with the instructor or the instructor with the course, depending on the projection on a spatial attribute case. Now we will talk about the enumeration of the evaluation of expression. That if we have evaluated a transformation from an expression E to E dash based on some rules, that is EI, so we cannot have E and E dash equivalent to each other if there is no rule EI present to it. So except for EI, we can have all the enumeration of E1 that is belonging to the E1 dash. Now how to do that using the algorithm? We are producing the algorithm for the enumeration of evaluation. Now, it is also not necessary to generate every possible expression that can be generated on some rules EI. We should generate only the expression in that much level that will suffer from all the query optimization and also the ordering of the joining and the attributes on the joining. So if these are expressed in one evaluation of the equivalent expression, then there is no need to generate more expression to this, because our motive is to optimize the query processing, not just generating relational expression or transform them to a subquery. So here we are describing a procedure that is gen all equivalent. That means it will generate all equivalent expression of an E. So first my equivalent is the set of E. That means it will consider only one expression E. And now we will generate one equivalent expression and add it to the set of E. Now we need to match every EI that belongs to EQ. That means EQ is containing all the set of E, EI, E1 to E2 to EN. So first we are taking one EI that it is belonging to EQ with the equivalent rule RJ. So if it is satisfying some rule RJ, then we need to perform the next. Now, if there is any sub-expression EI of the particular expression EI, that means the smaller EI is containing the sub-expression. Say for the teachers, that is joined with the instructor based on the selection department name equals to music. So, if it is matching any one side of RJ, we know that the equivalent rule has two sides. If it is matching any one side, then we should check the other side is being matched or not. Now, if it is matching one side, then we need to create an expression that is E dash, which is equivalent to EI except the sub-expression small ei that is being transferred to match the other side of RJ. That means the small ei, if it is matching one side of RJ and has been transformed to the other side of RJ, then other than that particular sub-expression EI, we can have the equivalent expression E dash of the EI, and that we are creating. Now we need to add this E dash to the EQ if it is not belonging to the EQ. So somewhat is possible that already the expression that we are finding without the sub-expression that is used for matching to the other side of a rule already present into the equivalent set. So if it is present into the equivalent set, no need to redundantly add it. We just have the new E dash added to EQ if it is not present. So we will perform this one until there is no more expression that we can add it to this EQ. So in this way, we can perform the enumeration or this ordering of the expression in the equivalent set. So that is all for today. Thank you for watching this video. Stay tuned with Ekeeda and subscribe to Ekeeda.